calculator is developed using the Muskingum-Cunge method to solve the classical Thomas problem of flood routing. To enable it to study the effect of runoff diffusion, the calculator varies 1. Peak inflow, 2. Time base, and 3. Channel length. For peak inflow, the choice of Q sub P in CFS per foot is A. 200, B. 500, and C. 1000. For time base, the choice of T sub B in hours is A. 48, B. 96, and C. 192. For channel length, the choice of L in miles is A. 200 and B. 500. The results are in close agreement with existing analytical solutions of the Thomas problem. The Thomas problem, 1934, is a classical problem of flood routing. Thomas routed a sinusoidal flood wave through a unit width channel of length L equal 200 miles and slope S sub O equal 1 foot per mile. The base flow is Q sub B equal 50 CFS per foot. The peak inflow is Q sub P equal 200 CFS per foot. And the time base of the hydrograph is T sub B equal 96 hours. In this video, we describe an online calculator for the Thomas problem using the Muskingum-Cunge method. To enable it to study the effect of runoff diffusion, the calculator varies peak inflow, time base, and channel length. The choice for peak inflow, Q sub P, in CFS per foot is A. 200, B. 500, and C. 1000. The choice for time base, T sub B, in hours is A. 48, B. 96, and C. 192. The choice for channel length L in miles is A equal 200 and B equal 500. The Muskingum-Cunge method is a variant of the Muskingum method in which the routing coefficients are calculated based on hydraulic variables using the formulas derived by Cunge. The details of the methodology are given by Ponce, 2014. With reference to Figure 1, the routing equation of the Muskingum-Cunge method is, in which J equals spatial index, N equal temporal index, and the routing coefficients C sub O, C sub 1, and C sub 2 are calculated as follows. In which C is the Courant number, and D is the cell Reynolds number, with delta T equal temporal interval and delta X equal spatial interval. The discharge depth rating is, in which Q equal unit width discharge, D equal flow depth, alpha equal rating coefficient, and beta equal rating exponent. The flood wave celerity C may be calculated as follows. In the constant parameter Muskingum-Cunge method, the routing parameters C and D are calculated based on the average inflow discharge Q sub A. The average inflow discharge is kept constant throughout the computation. The original Thomas problem had the following specifications. Base flow, Q sub B, equal 50 CFS per foot. Peak inflow, Q sub P, equal 200 CFS per foot. Hydrograph time base, T sub B, equal 96 hours. Channel length, L, equal 200 miles. Channel slope, S sub O, equal 1 foot per mile. Time interval, delta T, equal 12 hours. Space interval, delta X, equal 25 miles. Rating coefficient, alpha, equal 0.688. Rating exponent, beta, equal 5/3. The value of Manning's friction coefficient, calculated from the rating curve, is n equal 0.0297. The online calculator resembles the Thomas problem with important extensions. 1. A choice of channel length, L in miles, A 200 and B 500. 2. A choice of peak inflows, Q sub P in CFS per foot, A 200, B 500, and C 1000. Note that this choice provides peak inflow baseflow ratios, Q sub P over Q sub B equal A 4, B 10, and C 20. 3. A choice of time base of the hydrograph, T sub B in hours, A equal 48, B 96, and C 192. The time-based multiplier adopted to determine total simulation time, or TST, in hours is 2.5. Therefore, the corresponding values of TST for the three selected values of T sub B are A 120 hours, or 5 days, B 240 hours, or 10 days, and C 480 hours, or 20 days. Table 1 shows the input data and routing parameters for the 18 possible combinations. 2 channel lengths L times 3 peak inflows Q sub P times 3 time bases T sub B. The parameter n sub t is the total number of time intervals. N sub x is the total number of space intervals. The temporal and spatial intervals shown in Table 1 have been judiciously chosen such that the Courant number is reasonably close to 1. This is necessary to preserve the accuracy of the numerical computation. Run 11 of Table 1 is presented here as an example of the use of the calculator. For this case, L equal 500 miles, Q sub P equal 200 CFS per foot, T sub B equal 96 hours. The results of the calculator online Thomas problem are shown in Figure 2. They are peak outflow Q sub PO equal 176.84 CFS per foot. Time to peak, T sub P equal 128 hours. For comparison, the analytical results obtained by Ponce et al. 1996 using diffusion wave theory are Q sub PO equal 176.74 CFS per foot and T sub P equal 127.82 hours. The agreement between calculated and theoretical results is remarkable. An online Thomas problem calculator using the Muskingum-Cunge method has been developed. The calculator varies peak inflow, time base, and channel length, enabling it to analyze the effect of runoff diffusion on the outflow hydrograph. The input choices are the following. Peak inflow Q sub P in CFS per foot, A equal 200, B equal 500, and C equal 1000. Hydrograph time base T sub B in hours, A equal 48, B 96, and C 192. Total channel length L in miles, A equal 200 and B equal 500. The results are shown to be in close agreement with existing analytical solutions of the Thomas problem.